AP Chemsters, this is Mrs. Vanderlei bringing you the 8.6 edition of The Blank Wall. And this is about the periodic trends in the size of atoms and effective nuclear charge. You may or may not remember from your first year chemistry class about these periodic trends, we start off with the size of atoms, but you probably never have heard of this idea of effective nuclear charge. So that's something new that AP Chemistry brings to the table here. So how can we explain the idea of periodic trends? Well, let's go back and take a look at section 8.5. What was 8.5 about? It was pretty quick, wasn't it? It was about the periodic law. And the periodic law says the chemical properties of elements are largely determined by the number of valence electrons they contain. Well, I could ask you another question. Well, what makes the number of valence electrons work? All right, what did we determine was true about the number of valence electrons? It all depended on where they were on the periodic table. So we could talk about this periodic law is the chemical properties of elements that are determined by where they are on the periodic table. And that's what we're going to see to be true for these section 8.6 about the atomic radii and 8.7. So let's go back and see what 8.6 has to say. Well, we're going to be talking about atomic radius, so we should probably define what the atomic radius is. And so atomic radius for the non-metals, it's half the distance between two atoms bonded together. So if here is, let's say, nitrogen and bonded together, and so here's the nucleus of one nitrogen and here's the nucleus of another nitrogen. It would be half that distance between those two. For metals, it's half the distance between two atoms next to each other in a crystal lattice. So that's just how we're going to use that as a definition. And let's take a look at this chart here. So this is data. We're looking at data here. And what can we conclude about the atomic radii? Well, we can look at the atomic radii in two different ways. We can see the atomic radii going across the period and down the group. And let's take a look at going across the period. So here's hydrogen, helium. Here is lithium all the way going down to neon. Here is sodium going down to argon. Potassium going down with a few little blips going down to krypton. So what is the general trend as you go across the period? The atomic radii goes down. It gets smaller. We can look at the data and say, yes, that lithium is a much larger atom than neon is. But what if we're to go down a group? Here, let me switch colors here. So if we're going to go down the group, so let's take a look at here is hydrogen. This is group 1. Lithium, sodium, potassium, rubidium. What's happening as you're going down the group? Atomic radius increases. I don't know why it just did that. And is that the only group it works out? No, you can look at the helium, argon, all the way here. Here's your noble gases. And we can also say those atomic radii are getting bigger as well. So that would be our trend as you go across the group. The atomic radii gets smaller. Please remember that. And going down the group, the atomic radius gets larger. I don't know what I was just doing there. So here, let's kind of go here. And let's scroll down and see what's going on. Ha! Look at that. It looks kind of funny. Hang on 1 second. So this is basically a rewording of what we just talked about. So as we move down a column, I don't know if you can see this, but I am about right here. As we move down the column or a family, the periodic table, the atomic radius goes up. So atomic radius increases. As we move right across the period or row in the periodic table, the atomic radius decreases. Okay, and so why, and I'm glad you asked, all right, so what we're about ready to teach you is this idea of the effective nuclear charge, and that's going to be our answer for a lot of these trends. If you recall your first year chemistry, we talked about attraction. It's all about attraction, and that still is true. We're just going to help kind of tweak that idea of attraction when we talk about effective nuclear charge. So let's kind of turn the page and see what I'm talking about. All right, so this is the effective nuclear charge. I wrote this is a very important section. Please get used to this, wording this correctly as the reasons for the trends. The AP will want to see that you can, talk intelligently about effective nuclear charge, okay? So please pay very, very close attention to this, okay? So let's check this out. The trend in atomic radius as we move right to the right across the period is determined by the, watch this, inward pull of the nucleus on electrons in the outermost energy level. So what is that really saying here? So if I have my nucleus full of protons, all right, and here is my electron clouds, if you will, or a whole bunch of electrons around here. All right, the trend in atomic radius as we move right to the right across the period is determined by the inward pull of the nucleus on the electrons of the what? Outermost energy level. Okay, so what's the attraction going on here? Well, do you remember what we talked about earlier? If I'm talking about, let's say, anything in the second shell, what's standing between the nucleus and the outer electrons? Well, the inner electrons are standing in between, okay? And we're going to see that there was shielding going on and repulsion going on, and that has something to do with it, okay? So keep that in mind. It says, according to Coulomb's law, do you remember what Coulomb's law? The energy is equal to KQ1 Q2 over R. Do you remember that? The attraction between a nucleus and electron increases with increasing magnitude of nuclear charge, meaning how many protons it has. So the more protons, in a sense, the more of the positive charge there's going to be. But keep in mind that the electrons are, staged in different places, and there are some that are really far away. So what kind of attraction will they have on those outermost electrons? So think about that. Here's an example. We're going to talk about hydrogen and helium, for example, because, it's kind of simple here. Hydrogen has what? One proton and one electron, all in the first shell, and it says it takes 12 kilojoules per mole of energy to remove this one electron, okay? But look at the next one. What's different here? We have a helium plus. It has two protons and one electron. How do I know it has one electron? Because it has a charge of +1. One electron has been removed. And so it says it takes a lot more energy, almost 4 times as much energy to remove this electron. Why is it so much more difficult to remove this electron from helium than this electron from hydrogen? Well, I think you're going to see it has to do with that there are more protons in the nucleus of helium. So let's put this together here. Effective nuclear charge experienced by a particular electron in an atom is the actual nuclear charge, that's your number of protons, minus the charge shielded by the other electrons. This is your inner electrons. Let me write that down. So they do have some symbols here. Z, effectiveness. Z has always been the atomic number in symbols, I guess, is equal to the number of protons minus the inner electrons. And I don't know why they call the S, maybe because it's being shielded. Don't know. It says core electrons shield electrons in the outermost principal energy level from nuclear charge, but the outermost electrons do not efficiently shield one another from a nuclear charge. So if I have, here's my nucleus in here with a bunch of protons, and here's my inner electrons, here are my outer electrons. What they're saying that these inner electrons are effectively shielding these outer ones, but the electrons over here are not shielding each other, okay? It's only the inner electrons that are shielding, that are blocking those electrons, okay? So what does it say here? Summary of atomic radii. Moving down a column in the periodic table, the highest energy level of electrons increases, resulting in more orbitals and larger atomic radii. Moving across, I've already underlined some of this stuff. It's pretty important. The effective nuclear charge, why don't you underline this, by the electrons in the outermost energy level increases, resulting in a strong attraction between the outermost electrons and the nucleus and the smaller atomic radius. Okay? So to problem number 5, which electrons experience the greatest effective charge? So let's look at A. We're talking about the valence electrons in magnesium. You don't have to do this for all, but I'm just going to prove a point, okay? So let's go back and look at the electron notation, or the electron configuration, there we go. For magnesium, we start off with 1s2, 2s2, 2p6, 3s2, okay? So where are my inner electrons? Remember how what section 8.4 said, can you count? So can you count? What's the biggest number? 1, 2, 2, or 3? Well, hopefully you'll say, well, 3 is, and that's true. So these are my inner electrons. Okay, so Z effective is equal to Z minus S. Well, how many protons does magnesium have? Magnesium has 12 protons. How many inner electrons does magnesium have? Well, count. How many total electrons are right here? Can you count? 2 plus 2 plus 6. That's 10. So what's the effective nuclear charge for magnesium? It's 2. Okay. Let's try aluminum. Okay, well, what's the electron configuration for aluminum? 1s2, 2s2, 2p6, 3s2, 3p1. Hopefully remember how to do that. Okay, now what? So Z effective is equal to the number of protons minus the inner electrons. Okay, where are my inner electrons for aluminum? It's the same set of inner electrons. So how many are here? Well, what's 2 plus 2 plus 6? That's 10, right? But how many protons does aluminum have? 13. This is atomic number, isn't it? So what does that become? Well, what's 13 minus 10? That's equal to 3. So right now you can say aluminum has a greater effective nuclear charge than magnesium does. So we still have to look at sulfur, don't we? Isn't that my next one? Yes, sulfur. So let's look at sulfur. And here we go. That's 1s2, 2s2, 2p6, 3s2, 3p4. Okay, so where are my inner electrons? Again, what's my biggest number? 1, 2, 2, 3, or 3? I think you're going to find out 3 is my biggest number. Those are my valence electrons. And so here are my inner electrons there. So we can do the effective nuclear charge is equal to number of protons minus the inner electrons. Well, for sulfur, I believe it's 16 is the number of protons sulfur has. I still have 10 inner electrons, so the effective nuclear charge for sulfur is 6. Do those numbers ring a bell? Yes! Can you see that the effective nuclear charge is the same number as the number of valence electrons? How's that grab you? Hopefully that makes sense for you. So what does effective nuclear charge do for us? If you have a greater effective nuclear charge, watch this. The effective nuclear charge, I'm back over here again. The effective nuclear charge by the electrons is what? Resulting in a strong attraction, okay? The greater the effective nuclear charge, the greater attraction. And if you recall what was said in your first year chemistry class, the greater the attraction, the smaller the nucleus, okay? I've used the examples of, watching the students around this time of year. It's prom time. You know who's attracted to whom, because you can see how close they stand to one another. The greater the attraction, the smaller the space, okay? They're going to come together a little bit more closely if there's great attraction. If there's very little attraction, you're going to stand a little bit further away from that certain someone, okay? So it follows the same idea. I get attraction, okay? So the more attraction, the closer you are. The closer you are, the harder to separate, and that's what we were looking at when we saw the energy it takes to remove. The greater the attraction, the harder it is to remove that electron, and that's what the effective nuclear charge is all about. Let's go on to the next section, or I'm sorry, the next page. Okay, we're not done yet. It's atomic radii and the transition elements, okay? Why do we need to look at the transition elements? Well, if you go back and look at this, what do you notice in here? These are your transition elements, okay? So there's a little bit of a blip in these guys, all right? And so not much of a change, but you can see there's a little bit of a change. So what's going on here? Well, let's try to find that out. It says, here we go, transition elements remain roughly the same size going across the period. That's a period, okay? And does that make sense? Does that look like what was going on here? Are these roughly, come on down, are these roughly of the same size? And yeah, that's fairly true actually, okay? The first one, Scandia, may be a little bit bigger. The first one down here might be a little bigger, but overall, once you get into this general area here, they're about the same size. Not perfect, but pretty close. So what's going on here? Why? Why is there not a big change like there was earlier? This is the number of electrons in the outermost shell remains the same. 4s is in the outermost shell, and after you fill in 4s, you go back and you fill in an inner shell of the 3d. Okay, so let's take a look at, how about my favorite element, vanadium? Okay, maybe we could quickly do that shortcut, and I believe, what was that going to be? Argon. I hope it is anyway. And that's 4s2 3d3. Okay, so the 4s electrons are your outermost, your 3d are your innermost. Okay, so how many electrons? Let's do this. So Z effective is equal to Z minus S. Well, I believe that's what, 23 is the atomic number of vanadium. Minus, okay, how many inner electrons do we have? Well, argon has 18, doesn't it? If argon has 18 and 3 more, that's 21. 21, inner electrons. And what does that equal? That equals to 2. So the effective nuclear charge of your transition elements is essentially 2. And that doesn't change as you continue filling them in. So the attraction remains pretty much the same throughout, because your effective nuclear charge is not changing. So let's check this out. On the basis of periodic trends, which atom is larger? Well, what does that mean? Do I have a lot of attraction or do I have small attraction? If I have a larger atom, that means I have small attraction. Okay, and what does that mean? If I have smaller attraction, tell me about effective nuclear charge. I have a lesser effective nuclear charge. Okay, so if I'm going to look at nitrogen versus fluorine, okay, my effective nuclear charge, so Z effective for nitrogen, would you agree is 5? And Z effective for fluorine, isn't that 7? So which one has small attraction? It's the one that has the smaller effective nuclear charge. So that would be the nitrogen. So this is what you need to say. Nitrogen is larger because, I'm going to kind of do a little shorthand here, the effective nuclear charge is smaller than, make it nitrogen, fluorine's effective nuclear charge. Therefore, it has less attraction. Therefore, it has a greater atomic radius. Okay, so I did a lot of shorthand, but hopefully you can kind of figure out what I'm trying to say here. So I'll say it one more time. So nitrogen is larger because its effective nuclear charge is smaller than fluorine's effective nuclear charge. 5 is less than 7. Therefore, you have less attraction. Therefore, you have greater atomic radius. Okay? Think about that. Now, nitrogen and fluorine are in the same period. So you talk about effective nuclear charge when they're in the same period, because if things are in the same period, that's going across, right? You're going to have a different number of valence electrons, you're going to have a different effective nuclear charge. Look at number 2. Hang on, let me erase what I've done so I have more room to write. Now, find carbon and find germanium. What do you notice about that? Hey, they're in the same group. I'm going to write that down. Same group. So if they're in the same group, what do you think is going to happen to their effective nuclear charge? They have the same effective nuclear charge, okay? So you can't answer the carbon and germanium if they're in the same family, if they're the same vertical family. You're not going to use effective nuclear charge because it's the same. They're both 4. So then what? Well, all you have to do is which one is larger, which one has more shells. So you're going to say germanium is larger than carbon because germanium has more shells. Okay, think about where germanium is. I believe it's in the 4p, and carbon's in the 2p. You have a greater atomic radius because you have more shells. Okay. Now look at number 3. I think we have a little bit of a problem in number 3. And nitrogen and aluminum, they're not in the same period. They're not in the same group. So what do you do? Well, let's go back and look at this one more time and see if we can't come up with a generalization. It's not perfect, okay, but maybe we can come up with something. So if I were to find nitrogen, here's lithium, beryllium, boron, carbon, here's nitrogen right there, and sodium, magnesium, and aluminum. So which one is bigger? What's going to win out overall? And the answer is the more shells overall, you're going to have the greater atomic radius. Okay, I think you can kind of see that. So here's argon, okay, down here. So even though it has the greatest effective nuclear charge, it's bigger than most of the elements in the period before it, okay? Not lithium and not beryllium, but it's bigger than practically everything else, okay? So the general term here, I would go as a rule of thumb, is that if you have more shells, it is going to be bigger. That's not a perfect answer, but it's the best we can give, all right? There's no better answer than that. So I would pick aluminum because it has more shells. Oops, I can't spell though. More shells, therefore greater atomic radius, okay? What about aluminum or germanium? Well, it's kind of a similar thing, but if you were to look at on a periodic table, let me go back to a periodic table. Okay, so here was your nitrogen, and what was the other one we're doing? Aluminum, I think. All right, so when you're looking at the trend this way, again, you're going to pick more shells. But what about the other one? Let me use a different color. Okay, so oops, I need to go one more over. Okay, we're going to be doing aluminum and germanium. Okay, so let's kind of look at the periodic table with aluminum and germanium. Okay, so we're looking at these guys. Anything strike your fancy here? Which one's going to be bigger? Again, we're looking at more shells with germanium, which will help, but it has a greater effective nuclear charge than aluminum. Here, aluminum has a couple things going for it in the problem above. Between nitrogen and aluminum, it has more shells and a lower effective nuclear charge. The effective nuclear charge for aluminum is 3. Effective nuclear charge for nitrogen is 5. So if you look at it both ways, aluminum is going to be bigger than nitrogen. But if we're going to go in a diagonal this way, holy cow, that's going to be a hard one to predict, because germanium has more shells, but germanium also has a greater effective nuclear charge. So which one's going to win out? I would once again look at the trend over here. Here is aluminum in this one. That's aluminum. And germanium is 1, 2, 3, 4. Oh my. They're about the same, aren't they? So is it really a clear-cut picture if you have more shells, and which makes it bigger, but you have a greater effective nuclear charge, which would make it smaller? So they're about the same, aren't they? That's not a very fun answer, and it's kind of a toss-up. So I would say, only because I looked at the chart there, that germanium barely does. It has more shells. But you got to be careful when you're going in the diagonal that way. all right, it's really kind of the diagonal like this. It's really hard to determine, okay? That's a problem. I don't think the AP is going to, you know, have you try to do one of those, okay? If the diagonal is going this way, yeah, you should get it. It's more shells, and it has a less effective nuclear charge, so it's a win-win situation there. So what about tin and iodine? Well, let's take a look at where tin and iodine are. So here's tin. Oh, thank goodness they're in the same period. Okay, so this is going to be a no-brainer. They're in the same period. Okay, so what we can look at is their effective nuclear charge. And so you could say that tin has an effective nuclear charge of 4, where iodine has an effective nuclear charge of 7. So you can say that tin has a less effective nuclear charge, therefore less attraction, therefore greater atomic radius. Okay, germanium or polonium, let's take a look at that. Let's go back to our periodic table here. So germanium or polonium. Well, once again, you're at this diagonal. I think what's going to help us out is that polonium is at least 2 shells bigger. So my guess is that polonium is going to be a larger than germanium, and let's take a look. Here is germanium. Over here is going to be polonium, somewhere around here again. Actually, it's going to be hard to tell. I'm sorry, that's not, polonium is going to be over here. So I think it's going to be higher. That's not going to be polonium. So I do think it's going to be higher than the germanium. But again, you know, it's not necessarily a clear-cut answer. But if I had to take a guess, it would be polonium because it's 2 shells bigger, and that will be more helpful. All right, so more shells. Now we have chromium and tungsten. So where are they on the periodic table? Chromium and tungsten. Oh, phew, they're in the exact same family, so they have the exact same effective nuclear charge. So which one's going to be bigger? Hopefully you'll say tungsten is. It has more shells. Finally, I think we have one more. And the answer is, so tungsten was fluorine or selenium. Okay, so which one is bigger? Now this should be kind of a no-brainer, I'm hoping. All right, so we have fluorine here and selenium here. We have a diagonal going this way. So it should work out to our advantage. Why? Selenium is going to be bigger for 2 reasons. It has more shells, good, and it has a lower effective nuclear charge. Selenium is 6. Fluorine is 7, so it has 2 reasons, okay? So I would say selenium has a less effective nuclear charge. Okay, 6 versus 7, and more shells. Therefore, it has less attraction. Therefore, greater atomic radius. Okay. So what about the next problem? I think this is the end of section 8.6. Yes, it is. So arrange the elements in order of decreasing atomic radii. So where are these? We have sulfur, calcium, fluorine, rubidium, and silicon. Let's go back and look at that periodic table. So we have, let me clear what we have here. Come here. Oops, no, don't do that. So we have this. I've already forgotten them. All right, so let me circle what we do have, okay? So which one is our biggest, okay? Hopefully you can see it's going to be rubidium. Why? 2 reasons. Most number of shells, and it has the lowest effective nuclear charge. Rubidium has an effective nuclear charge of 1. Calcium has an effective nuclear charge of 2. So which one's going to be bigger? Rubidium is going to be bigger because it has more charge, more shells and a smaller effective nuclear charge. So then what? I would say calcium would be the next one because it has more shells than fluorine, silicon, sulfur, and it has a little bit greater nuclear effective nuclear charge than rubidium, but a smaller one than silicon and sulfur. All right, so now what? Let's look at the, between silicon and sulfur. Which one is bigger, silicon or sulfur? Hopefully you'll say they're in the same period. So hopefully you'll say silicon is, okay? Why? Because the effective nuclear charge of silicon is 4. The effective nuclear charge of sulfur is 6. So silicon has less attraction because it has a lower effective nuclear charge. Therefore, it's going to be bigger. So then sulfur is next. And our smallest one is fluorine. Why? It has the fewest number of shells and it has the greatest effective nuclear charge at 7. Okay, so that would be my ranking for problem number, whatever that was. Well, let's find out. What was that problem? Okay, so number 7. So I'd say rubidium is greater than calcium, which is greater than silicon, which is greater than sulfur, which is greater for fluorine, okay? Most shells and lowest effective nuclear charge. This has the least shells, so it's smallest, and it has the greatest effective nuclear charge. So that's it for section 8.6. Please go ahead and go watch 8.7 next. I guess I'll end today with "Don't wait to be great," to quote the great Montel Brown.